We're going to work a few problems from topic 8, specifically 8.1 on energy production. These first four deal with 8.1. The others we'll do later from section 8.2. We have these IB problems. They're a little old, but I think that they still apply. We start with a reactor that produces 24 megawatts of power at the efficiency of 32%. We want to know how many uranium-235 nuclei we need to burn, to fizz, in order to generate this 24 megawatts at 32% efficiency. Okay, let's take this information over here. And since we have a 32% efficiency, then that means the 32% of our input power, or the fuel that goes in, we need to be able to generate this amount X. And what we're going to get out at 32% efficiency is going to be 24 megawatts. So the amount that we need to generate then is going to be equal to 24 megawatts divided by our efficiency. And that turns out to be 75 megawatts. That's how much fuel we're going to need, and we're going to lose 68% of that from different places, and only get 32% out. Now, in order to get 75 megawatts, well, that's 75. Remember, that's 75 megajoules every second. And to figure out how much energy we need, how much uranium we need to produce this much energy in a year, well, we have to multiply this by the number of seconds in a year. So we have 75, and that's megajoules, so that's 10 to the 6th joules, and there are 60 seconds in a minute, 60 seconds in an hour, 24 hours in a day, and roughly 365 days in a year. If you multiply all this out, you should get somewhere in the neighborhood of 2.37 times 10 to the 15th joules. All right, so that's how much energy we need. Now, each uranium nucleus, when it splits apart, we have that it generates only a very small amount of energy, 3.2 times 10 to the negative 11th joules. So that's going to tell us if we take this amount of energy here and we divide it, so we take our 2.37 times 10 to the 15th joules, and we divide that by the 3.2 times 10 to the negative 11th. And this is going to be with joules per nucleus, isn't it? I'll just say per N. This number turns out to be about 7.4 times 10 to the 25th. Okay, well, that's a lot of atoms, but atoms are very light. And how do we figure out? We want to know how many kilograms. So this would be the number of nuclei. What we can do is we can look in our formula booklet, and we recall that the mass of your average nucleon is about 1.67 times 10 to the negative 27th kilograms. So this is the neutron and the proton have a weight of roughly this. Each nucleus has 235 nucleons. So that's going to be 235 times the number here, right? Times this number, which I'll be lazy and just use an arrow. And that's going to be times this number here. I'll put in times 1.67 times 10 to the negative 27th. And that's kilograms per nucleon, 235 nucleons per nucleus, and then this many nuclei. This number now turns out to be about 29, and I got 29.06, I think, in my calculator. So it looks like we need to, looking through the problem, 2 sig fig seems to be appropriate, and so that we've got that there. That is the answer to number 1. This is number 1A. Okay. It also asks us over here, it says, I'm going to need another. Okay. It also asks us in the question here, during its normal operation, the following set of reactions take place. We have a neutron coming in and hitting an atom of 238, and then going to 239, so on and so forth. Well, first of all, I feel like they should have uranium 235 here. That's the reaction that's what we have. At any rate, here if we have a mixture, of course, of uranium 238 and 235. Maybe they're more concerned here with the heavier isotope. When that absorbs a neutron, it can split into neptunium and also plutonium. Comment on the international implications of the products of these reactions. So here I think I'll just say that what we have is very dangerous material, highly radioactive, highly poisonous, and also can be used to make nuclear weapons. Plutonium was the element used in the second atomic bomb. So definitely want to make sure that we keep dibs on that. So commenting on that, it can be used for other types of nuclear reactors, but it's a dangerous material. It can be used to make weapons, and it is also poisonous. Okay, number 2. The diagram shows a pump storage power station used for the generation of electrical energy. Water stored in the tank falls through a pipe to a lake through a turbine that is connected to an electricity generator. The tank is 50 meters deep and has a uniform area of 5 times 10 to the 4th square meters, and the height from the bottom of the tank to the turbine is 310 meters. The density of water is 1,000 kilograms per cubic meter. Show that the maximum energy that can be delivered to the turbine by the falling water is about 8 times 10 to the 12th joules. Okay, there's the information. Pause that if you need to. And let's start solving it. We need to find the volume of the water and multiply that by the density to find the weight of the water. And then we'll use the equation that the potential energy here is, the potential energy, of course, is mgh. Okay, and we need to know the mass. Well, the mass is going to be equal to the volume of the lake times the density of water, and it is 50 meters deep, so that's 50 times 50 times 10 to the 4th. This is the area times the depth, so that's the volume of the water. And then we have times the density of water, which is 1 times 10 to the 3rd kilograms per cubic meter, a ton per cubic meter. I don't really need that 1 there, but so this is all going to come out to be, let me keep going. Now, this is just the mass part, okay? This is the mass part here. So this is M, and then we've got G, we could say 9.81 meters per second squared, and then the height in the problem is 310 meters. Okay, so this is all going to multiply out to be about 7.6 times 10 to the 12th joules. And if we're looking at 1 sig fig, then that's roughly what they ask us to show, 8 times 10 to the 12th joules. 8 trillion joules. Okay, and this is number 2. I keep forgetting to write the problem. This is number 2A. Part B. Part B says the flow rate of water in the pipe is 400 cubic meters per second. Calculate the power delivered by the falling water. All right, well, I could also just come here and say, so the power is going to be mgh. The energy is going to be mgh. The power would be, you could think of it as mass per second. So I just have to say, if this is the energy falling, the potential energy is mgh, well then the power, so I'm going to say the power, I'll write that out not to confuse it, we could say is going to be, we could say the mass per unit time. That's not meters per second, that's mass per second. Let me write that out to make that clear. That's what we're told. We're told the We're actually told the volume, but we know the density, don't we? So I could take the mass per unit second, and then that's going to be times the G and the H. Okay, so finishing this out, I've got 400 cubic meters per second. So that's 4 times 10 to, that's the volume of the water times the density of the water. And this is going to be, remember, per second. So it's 400 cubic meters per second times 1,000 kilograms per cubic meter. And this is going to give me 4 times 10 to the fifth kilograms per second. And I multiply this times G, 9.81, and times H, 310. And then this should turn out to be about 1.2 times 10 to the ninth. And that's in watts now, because I'm looking at a flow rate. All right. I'm going to pause here for a moment and let you get a moment to confirm these calculations. All right. Let's now go to the next question. Number three, we have a source of energy loss for a pump storage power station. Here we are. We've got several different sources of energy loss. We've got friction and turbulence in the water pipe, friction in the engine and the turbine that creates the electricity, and then loss from the heating of maybe the electrical components due to the resistance in them. Calculate the overall efficiency of the conversion of the gravitational potential energy to electrical energy, and then we want to sketch a Sankey diagram. Okay, well, the first one we can just add up really these efficiency. This is energy loss, and it's already given as a percent. So 27 plus 15 plus 5, that's going to be 47. So we lose 47% of the energy. So our efficiency is going to be the part that we don't lose. So for number 3 here, number 3A, since we added these up and we got 47, that means the efficiency is 53%. And then we lose 47% through those 3 processes. We want to represent that as a Sankey diagram. And now, normally, hopefully, you'll be given a grid. These don't have to be super precise. It's a visual way of visualizing the losses at a glance. So they don't have to be super accurate, but they can't be wildly inaccurate either. They have to be at least proportional. We want to start with, 100%. So we start with a line, the width of an arrow. And remember, this is going to represent all the energy, 100% going in. You don't have to write this 100% here. And then as we go along, we lose energy. And then this goes all the way through. The first amount of energy lost is the friction and turbulence. It's 27%. So I need to make an arrow that goes down here that is somewhere in the neighborhood of, about a quarter of the original line, so that there is this idea of scale. You don't have to get out a ruler and measure this and take exactly 0.27, but you want to get a decent estimate. And this is going to be from the turbulence. So we need to label that turbulence of the water. All right, we go through, we continue with the process, and then we lose about 15%. So this next arrow needs to be about 0.15 of this original input over here on the left. So we come up a little bit more, and I'll say something like this maybe. And this is due to friction. And then finally, I come over here and I've got 5%. So it's kind of small. This goes out to heat. And I come up here and I'm left with, I should be left with 53% of the energy making it through to electricity. So it may not be exact, but I lose 47%. So this width right here should be about in the neighborhood of 53% of this original width right here. That's the idea. It doesn't have to be precise, but it needs to be rough so that you can see. You can't just sketch this any old way and have the heat arrow bigger than the turbulence arrow. That's where you would lose marks. So make it look at least somewhat proportional and to scale. And that's number 3. We got the Sankey diagram. Okay, let's go on to number 4. Number 4 says we have a nuclear power station and it uses uranium-235 as a fuel. We want to outline the process and energy changes that occur, which the internal energy of the working fluid is increased. And we want to outline the role of the heat exchanger of the reactor and the turbine in the generation of electrical energy. Okay, this is all down here, number 4. And then we want to identify one process in the power station where energy is degraded. And this would be one of the downward facing arrows on our Sankey diagram. We don't have to make a Sankey diagram here. Well, I'll direct your attention to the slides we did in class. We had a really neat little GIF that outlined this. I think it was slide 41. And let's see, here it is. Here's the GIF at least, courtesy of Mr. Lund, who made these slides that we've been looking at. This is an animated diagrammatic representation of how a nuclear power station works. So you can see over here that you've got your control rods, and in here we're also going to have our moderators. And over here in the red and the orange and the yellow, this is where the nuclear reaction is taking place. Cycling through with these red lines would be the coolant. And that could be, in some cases, it's molten salt. It could be molten sodium, maybe water. But going on inside of the actual reactor, you have a ton of heat being created. The neutrons are flying around. They're causing more and more atoms to split. As the atoms split, they generate more neutrons and kinetic energy. This kinetic energy is captured. It makes the fuel itself heat up. It makes the control rods heat up. It makes the moderators heat up. Everything gets hot. And as you cycle this coolant through the hot fuel rods and control rods and the moderators, you find a way over here with the blue to send it through a heat exchanger. And so the hot coolant goes to this heat exchanger. This heat exchanger, basically, this is a water heater. It's a boiler. It boils this water. And then as you can see up here, the steam generation, the steam generator is going to create the steam, which runs through this turbine. The turbine spins a generator, a coil, and a magnetic field. Then the steam is condensed back into water and the cycle starts again. In order to condense this water, we have yet another cooling system. And then this water over here coming in from the far right and cycling through is going to warm up too. And it's going to go out, and sometimes it's just dumped, or it could be used to heat further things as well. So once this process is done, we have a means of taking nuclear energy and creating thermal energy through the the kinetic energy of the particles flying out of the nuclear reaction. That energy is captured and transferred into water, which is boiled, then transferred into the kinetic energy of the turbine, and then that kinetic energy is put into electrical energy. and then that's sent out through the home to the homes and to the businesses. All right, so for our purposes here, I won't write all that down. Hopefully that made sense, and the diagram is a very handy way to look at that. Part B says identify one process in the power station where energy is degraded. There were several. There is the heat transfer from the coolant to the water. Heat's going to be lost in the walls of the reactor and the walls of the boiler. There's going to be friction loss when that steam goes to turn the turbine, which in turn turns the coils. Heat is obviously being just thrown away as the second cooling system recondenses the water, and if that heat's just dumped, that's an energy loss there. There will be energy loss in the transmission of the electricity out through the wires. So there's several places where you could find your answer for 4B, and that would also translate into, if you were drawing a Sankey diagram, that would translate into these arrows here on this Sankey diagram. You could draw a Sankey diagram for an electrical, for the nuclear power plant as well. That's it for 8.1. Next video will be about the second topic, the second subtopic in topic 8, where we will look at the thermal properties, mainly of the Earth, greenhouse gases, global warming, tidal energy, that kind of thing. All right, see you then.